This is David Van Vranken here at UC Irvine. I want to welcome everybody to the 13th lecture here in the Chemistry 51C series. I wanted to start off our lecture today talking about a series of news articles that I saw touted on Google News, where NASA scientists have discovered this strange molecule on the moon of Titan. And astronomers tend to point telescopes out into space, and then they attach spectrometers to them so that they can look at IR stretches and various spectroscopic signatures. So I thought it might be interesting to talk about spectroscopy out in space spectroscopy. The article talks about a very weird molecule in the atmosphere of Saturn's moon, Titan. And it says, which sounds somewhat compelling here, that it could point to alien life. Wow, that sounds pretty dramatic. Let's go and take a look at what they did. The molecule that they said they found evidence for is a molecule called Cyclopropenylidene. And that deserves some discussion because it's immediately apparent from the name that ends in "ene" here. It's not just an alkene. The name ilidene here suggests that it is a member of a class of compounds called carbenes, where the carbon only has 6 electrons. Now, you've seen, in order to give us a frame of reference here, I want to talk about a related molecule that was mentioned in one of the problems in chapter 17 on aromaticity and aromatic molecules. That's in the 5th edition of the Gorzynski-Smith textbook. And the molecule I want to first discuss is called the cyclopropenyl cation, because it's an aromatic molecule. And I just want to remind you about the requirement for what does it mean for something to be aromatic and have this property of aromaticity. So organic compounds that have this property of aromaticity are aromaticity. There we go. Aromaticity are cyclic. They are composed of a cyclic array of double bonds and p orbitals, and in them they have a very specific number of electrons in order to satisfy this criterion of aromaticity. They need to have 2 electrons in that cyclic array, or 6 electrons in that cyclic array, or 10 electrons in that cyclic array. Anything that satisfies this 4n plus 2, where n is some sort of whole number. So let's go ahead and count up the electrons here. There's 0 electrons in this empty p orbital for that carbocation, and there's 2 electrons over here in this pi bond. So that's 2 electrons. So this satisfies the properties of aromaticity. It is a carbocation, but it is unusually stable because it's aromatic. Now, cyclopropenylidene is kind of like this cyclopropenyl cation. So here's the molecule that they discovered in the atmosphere of Saturn, at least what they're saying here. When I looked inside the paper that they referenced, I did not recognize whatever form of spectroscopy that they're using here. Like, even the units for frequency were not what I recognize to be in the normal infrared region. So I'm not sure what properties they're looking at even. Are these stretches or, microwave spectroscopy looks at rotations but doesn't tell you any functional groups. So here on Saturn, they've discovered this molecule cyclopropenylidene, and it has this carbon here it has a carbon atom right here that is referred to as a carbene. It's a very unusual species. It's right. Notice that carbon has 2 single bonds and then a lone pair. It's only got 6 electrons. That's weird to see carbon atoms with only 2 bonds to them and no more. So let's go ahead and talk about bonding in a carbene like cyclopropenylidene. I've left out one of the double bonds here, so let me draw that in. So let's take a look at that carbon atom in cyclopropenylidene. It clearly has a lone pair, but what's up with this missing? How come it doesn't have 8 electrons? There must be some sort of an empty p orbital on there that makes it like a carbocation. So I've indicated that over here on this carbon atom. I've indicated that empty p orbital by drawing an empty p orbital and a positive charge. But that means that sticking out on the edge of this molecule, there's a lone pair just kind of jutting off to the side, out into the side of the molecule. That's kind of like a carbanion. So this carbon atom here is kind of like a carbocation and a carbanion at the same time. So it's net neutral. So we don't draw the charge over here on this carbene-carbon. And so that's really weird. How can something be like a carbocation and a carbanion? And organic chemists make this type of reactive species under a variety of different conditions. They're called carbenes. They're extremely reactive, and it's just a weird molecule. These types of carbene species, they tend to undergo reactions where quite often they act as nucleophiles and electrophiles at the same time. So here's this. So again, this molecule they have evidence for, spectroscopic evidence for, on Saturn. I've got these two pictures of that carbene cyclopropenylidene for you. Now, I want to come back to the initial statement. They say it could point to alien life. The fact that there's this weird molecule, super unstable molecule, not because it's got a 3-membered ring, but because of the carbene makes it super unstable, does make it kind of weird. But when you're out in some sort of gaseous environment and you're not surrounded by solvent molecules, there's not a lot of stuff to react with. You don't collide very frequently when you're in the upper atmosphere of Titan. So I'm just going to go ahead and answer their question or address what they're really saying here by just simply saying, no, this doesn't point to alien life. There's nothing about this that suggests that it is important for alien life. Living molecules that you find in living systems tend to be stable molecules, not things that are so reactive that they react with every conceivable functional group. So let's go ahead and talk about our chemistry for today. We are entering a new chapter, and I probably should have drawn a picture here to get you what is this chapter about. We're starting a new chapter, chapter 22. We just finished an entire chapter on aldehydes and ketones. So imines, enamines, acetals, Wittig reactions. But in this chapter, we're talking about carboxylic acid derivatives, where attached to some sort of a carbonyl, there's a nitrogen or an oxygen or a carboxylic acid. An acid chloride would have a chloride there. And we're going to be substituting that group X with some other heteroatom. Could be another oxygen atom or an amine or a chlorine atom. So that's what this chapter is about. It's about substituting directly next to carbonyl groups. This whole chapter is going to be about this. Incredibly important. So in the beginning of the chapter, if you read through the book, they're going to introduce you to different functional groups where some heteroatom is attached to a carbonyl group. And you should already know these common functional groups. You've had them in spectroscopy. And we've talked about reactions of esters and amides and acid chlorides, acyl chlorides. So there's another sort of preview section in the book, if you read the textbook, that talks about structure versus reactivity. And I'm going to hold off on that because we're going to really go into that in detail shortly. And specifically when it gets to section 22.7 of the textbook. And then usually at the early part of the chapters in our textbook, they talk about IUPAC nomenclature. And I've already mentioned before, I don't ask you IUPAC nomenclature on my exams. And that's because IUPAC nomenclature is so hard for you to use that in a practical sense that I can't ask you the kinds of questions that will be meaningful. But some standardized exams take these rinky-dink little molecules and see if you could memorize the naming rules. Okay, so it's good for you to look through that. But what do I get out of an IUPAC name? Here's the kind of IUPAC name that you're going to be confronted with if you open up the prescribing information, that little paper insert that you find in every prescribed medicine in the United States. They'll have a chemical structure of something and an IUPAC name. And what can you get out of that? Frequently nothing of value, certainly nothing that you could answer for yourself. I tend to look at IUPAC names for typical organic molecules, and I can see there's an acetyl group. I can see there's a 6-membered ring with nitrogen. That's a piperidine. I see a benzothiazole, which is a benzene ring fused to a 5-membered ring with sulfur and nitrogen. I know the names of functional groups. The key functional group here is that this molecule refers to an oxidiazole. That's a 5-membered ring with 2 nitrogens and an oxygen. And I'm not exactly clear where the nitrogens, and I'd have to go look that up. So I would expect you to be able to identify functional groups in an IUPAC name. That way I can talk about, oh, see that ketone right there? Maybe you can add to that carbonyl group. That's kind of the level of which most chemists would be able to use IUPAC nomenclature. Now, as far as carboxylic acid derivatives, esters, amides, carboxylic acids, they talk about physical properties usually at the beginning of the book. Anything that has lots of heteroatoms will tend to be polar. Will have higher boiling points than just simple hydrocarbons. But I'm not going to ask you to memorize boiling points or things like that. So you can just kind of skim through that. I, for sure, am going to ask you spectroscopy questions on our exams. I always do ask at least one. And so I've already summarized some of that spectroscopy stuff, and we'll continue to practice those in our discussion section. So be aware, I do ask usually one spectroscopy question on the regular midterm exams. And maybe two if I can fit them in on a final exam if it's twice the length. There's another section at the early part of the book where they talk about some interesting esters and amides. They're all interesting to me, so maybe they talk about some common ones. That's just kind of fun reading, unless I'm not going to ask you to memorize the structures in that section just so you can repeat them back on the exam. So really the first part of this chapter is just kind of getting you ready to start talking about chemical reactivity. That's what I'm going to ask you about. I'm going to ask you about chemical reactions, solving problems using mechanistic thinking and thinking about chemical reactions, and then synthetic transformations. Let's go ahead and talk about some of the key transformations of carboxylic acids that you're going to see here in this chapter. So the first reaction that we'll talk about here is the transformation of carboxylic acids into acyl chlorides. And the reagents are very simple. It's reagents that you've seen before. It's thionyl chloride, SOCl2. You've seen that reagent before for turning alcohols into alkyl chlorides. And usually you did those reactions with pyridine. And that might have been back in chapter 10 on SN2 substitutions or something, or chapter 9 in the book. But here we don't use pyridine. Don't put pyridine. That was turning alcohols into alkyl chlorides. Here we're turning carboxylic acids into acyl chlorides, and the extra reagent is heat. And as the reaction is going, you're blowing HCl out the top of your reaction. And this reaction is money. My gosh, I can't describe to you how important this is. I'm just going to write here, money. That is total money, because acyl chlorides are the most reactive functional carboxylic acid functional group that we know of. Once you make an acid chloride, you can convert it to every other type of functional group, like amides, esters, carboxylic acids. You can even use them in Friedel-Crafts substitution reactions. So finally, we're telling you how to make acyl chlorides so that you can now use them in Friedel-Crafts acylation reactions. Boy, of course you have to know that reaction. How do you take a carboxylic acid and convert it into an ester? Well, there's a simple one-step set of conditions for doing that. If you just feel absolutely, in the laboratory, we'd probably make it from the acid chloride. But if you want to do it in one step from the carboxylic acid, what we do is we look over here at the ester. In this case, it would be derived from methanol. And then we use that as the solvent for the reaction. I'll write it backwards so it looks kind of like the alcohol functional group, like the carboxyl functional group. So if you run the reaction in methanol and then add a catalytic acid, and we'll go ahead and draw that out. Catalytic, what's a common acid? It needs to be a strong mineral acid, hydrochloric acid, sulfuric acid. Those are the common ones. Could be sulfuric acid, could be toluene sulfonic acid. If you couldn't remember HCl and you wrote it would work. But usually we're dumping a bunch of acid in there, not just a few milligrams of acid. So catalytic HCl, and then if you were trying to make an ethyl ester, you'd run the reaction in ethanol. Okay, there's a one-step procedure for converting carboxylic acids to amides, and it's not like these conditions here up above where we don't use those conditions. We have a separate set of conditions that also involves you looking at what's that functional group that we see on the amide that wasn't there initially. Well, it's dimethylamine. So if you want to make an amide out of the dimethylamine, what we have to do is write that out In this case, we only add one equivalent, so dimethylamine, and we're going to have a whole chapter on amines. But all you have to do is just recognize that this comes from diethylamine and add the other secret reagent. And the other secret reagent is DCC, not PCC. That's an oxidant. Forget PCC. It's DCC. And we'll get to that shortly. So that's the way you make amides. You just have to recognize what's that nitrogen-containing functional group and be willing to add that in as an amine. Okay, you can also make amides from anhydrides, and I'll have something to say about anhydrides shortly. This functional group over here is called a carboxylic acid anhydride. And it's named an anhydride because if you add water, it'll convert it to acetic acid. So it's kind of like acetic acid, that's where two acetic acids have lost water and come together. So it's quite frequent that you use anhydrides to make simple amides. In this case, in a similar way that we did up above, we're going to identify this functional group here. Okay, we need to make a phenylamide, an amide out of aniline. So the amine that we need to add here as our starting material is going to be aniline. This time I'll kind of write it with the phenyl first. It just feels more natural to me. And then we need something in here to soak up the acid that's present. And this is going to be the hard part for you to remember. And if we're doing this reaction, we need to use triethylamine to make amides. And that's going to be common also for acid chlorides, as we'll see later. Okay, finally, we can take esters and we can cleave this bond here. We can cleave this bond between the carbonyl group and this oxygen of the ester part. So, and you can see that we're creating over here, you can see that we're creating this leaving group. And what we're adding here is just a very simple reagent, and that's sodium hydroxide. And that turns out to be a pretty important process, enzymatically, synthetically, in a wide range of contexts. Okay, so you need to know those synthetic transformations for sure. Here, let's go ahead and follow up with another set of synthetic transformations where you don't start from carboxylic acids, but instead, or esters, but instead start with some other functional groups. So once you have an acid chloride, boy, you need to know how to make acid chlorides. Thionyl chloride and heat makes acid acyl chlorides from carboxylic acids. And if you want to take an acyl chloride and convert it to an ester, an amide, or back to a carboxylic acid, that's super easy. So over here, let's suppose we wanted to convert, let me try to make this more interesting. Let's suppose we want to make an isopropyl ester out of this, or any ester of any exotic structure that you want to make. I guess isopropyl is not so exotic. You just look at this part of the molecule, and then you add that alcohol. It's that easy. So in this case, I'll go ahead and write the alcohol here. This is isopropanol. I don't feel like I have enough room to write the word isopropanol there, so I'll just draw the chemical structure. But the reaction will generate HCl, and we have to soak up that HCl. And so in this case, we add a base that you've seen before that's good for just soaking up the HCl. It's not designed to make anions or deprotonate things like T butoxide. You were just trying to get something so the HCl doesn't build up in the reaction. Use pyridine. Again, that's a base that you used when you did thionyl chloride and pyridine. Way back in the earlier chapters of the book, chapter 9. Okay, we can also convert acid acyl chlorides into amides. All we have to do is just look at the structure of this amide here that's being formed, the carbon-nitrogen bond, and draw that amine substituent as an independent amine with an extra H on it. So if we're going to make phenyl NH, then add phenyl NH2, which is aniline. Now, we need to soak up the acid that's forming in this reaction. And the frustration here is that we don't use the same base that we did for alcohols. You know, for alcohols, we can use a pretty weak base, pyridine, but we need a stronger base if we've got amines floating around in our reaction mixture. And the amine that we're going to use to soak up the HCl here is going to be triethylamine. Let me just show you what's happening to these bases that we put into the reaction mixture. So over here on top, when we make the ester, we're adding pyridine. And the whole point of the pyridine is that we end up with this byproduct that nobody isolates this. We just don't want HCl to build up in the reaction. And so this is what's happening to that pyridine. It's just forming this salt gets washed away at the end of the reaction with the aqueous workup. Over here with the aniline, we don't want HCl to build up and protonate our aniline, and so we're adding triethylamine to soak up the HCl. And you want to make sure you're using a base that's strong enough that you don't protonate the amine. We can't use pyridine. That wouldn't be strong enough to soak up the HCl if aniline is present. So we throw in triethylamine, and it makes this triethylammonium chloride salt. So again, nobody uses this reaction to synthesize triethylammonium chloride or pyridinium chloride, but those are just byproducts of the reaction. In other words, if I drew a box and I said, draw the products in the box, I'd have to be very specific so that you only drew the amide and didn't draw the salts, or else I'd have to tell you, make sure you draw the salt byproducts or something. But we usually don't draw the salt byproducts. Okay, so if you have amides and esters, you can hydrolyze those right back to carboxylic acids. So how do you do that? You need harsh conditions. It takes super harsh conditions to cleave this bond over here of an amide. But this bond is not easy to cleave. That's why human proteins are made, or all proteins on the planet Earth are made with amide bonds. You know, the half-life for an amide bond in water just sitting around is about 7 years. Right? You don't want your proteins to hydrolyze in 2 seconds because all your cells contain water. And so we need harsh chemical conditions if you don't have an enzyme specifically designed to cleave that bond. In the laboratory, here's the conditions that it takes. You have to use 6 molar hydrochloric acid. It's not quite concentrated hydrochloric acid. Concentrated hydrochloric acid is 12 molar. But, you know, this is pretty close to 12 molar. It's like you dilute it 1-to-1 with water, and it's still pretty concentrated. And you have to boil it. So, the HCl is in water. So, that's the reagent that's being used to add HO and H. And you have to boil it at 100 degrees. If you wrote delta, I would understand what you mean, but we're not talking about heating to 40 degrees or 50 degrees or 60. Man, this is going up to the highest possible temperature you can and refluxing it overnight. It's hard to cleave amides. Man, it is so hard to cleave amides. And likewise, you have to use very similar conditions if you want to hydrolyze esters. I showed you on the previous slide that you could hydrolyze esters using sodium hydroxide. That's room temperature. But if you use these acidic conditions, it's exactly the same conditions you use for the amide. Then if you're doing the acidic conditions, you have to heat it in order to get that to work. Okay. So powerful transformations of carboxylic acid derivatives. This is what the chapter is. It's taking one carboxylic acid derivative, like an acid chloride, carboxylic acid, amide, ester, and converting it into another one, sometimes in one step. All right, let's go ahead and talk about this, the reactivity of amides and esters and carboxylic acids, and try to compare them to the reactivity of ketones and aldehydes. So a couple of chapters ago, when we were talking about hydridoaluminate reagents and alkylithiums and Grignard reagents, we said that once you made a ketone or an aldehyde, the nucleophile, these kinds of nucleophiles would usually add again. And so we ended up showing you, for example, that if you took an ester and a Grignard reagent, you would go all the way in those cases. You would go all the way back in chapter 20 to adding a second equivalent of the reagent, and you couldn't stop there. That's what we told you in chapter 20. So there was this unstoppable process where you couldn't stop adding a second time. Okay, but in this chapter, what we're going to tell you is that if you make derivatives where the nucleophile is oxygen or nitrogen, you stop after one addition. And that's distinctive. It's different from what we told you in chapter 20. So let me just kind of write this here again with this glorious purple here. So here in this chapter, here in this chapter 22, if nucleophile is equal to oxygen or nitrogen, you stop after one addition. And that may seem kind of weird and opposite. Let's go ahead and talk about that. What's going on with that kind of thinking? So what this chapter is all about is substituting. We're going to substitute, in this case, the ethoxy group for some nucleophile. And what's that mechanism? It's not one step. It's not one step, it's a two-step mechanism, and it will always be at least two steps in this chapter, at least. So sometimes more than two steps. So the reaction is going to start off with addition to the carbonyl group. Right? That's the way most organic chemistry works. Addition to carbonyls, and you push the electrons from the CO double bond up to the oxygen. Let's go ahead and draw out the next mechanistic intermediate that we get. So we'll generate this tetrahedral intermediate. And now this tetrahedral intermediate is unstable because there is an alkoxide anion on that central carbon atom. And it's trying to push downward and push out a leaving group. And there is a leaving group on there. It may not look like the kinds of leaving groups you saw for SN2 reactions, but if there's an anionic atom right next door with lone pairs, it's going to push that right out. No problems. That's super common. We already saw this when we were adding Grignard reagents and tetrahydridoaluminate hydrido groups. We've already seen this process before where O- can kick out alkoxides. O- can kick out hydroxide. O- or carbanion with a lone pair on carbon could do the same thing. So this is going to be tough for you if you somehow memorize that alkoxides can never act as leaving groups. That was because it was for SN2. So this is what we're doing in this chapter. It's always a two-step, at least two steps. Sometimes it's more than two steps, but you'll always find in those mechanisms addition to the carbonyl and then elimination of some sort of a leaving group. Those two steps are common to every mechanistic depiction for nucleophilic acyl substitution reactions. And let me just try to, let me go ahead and try to highlight this because this is what our chapter's about. This is chapter 22 in a nutshell. Right here, two-step, addition, elimination. Sometimes there's some proton transfers thrown in there as well, but there's always an addition to the carbonyl, and there's always an elimination of a leaving group. Now, let me just remind you, this is going to be so tough because you've spent about 8 months learning one-step SN2 reactions. Your whole brain is geared to think about SN2. It's like, wow, the book just loves that. Let me just tell you, this process where you go from one carboxylic acid derivative to another, it will never, ever go through a one-step mechanism, right? If it did, that would be called SN2, and it would have belonged in a chapter like 10 chapters ago or something. So don't ever, 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 ever do this. Don't ever try to take your nucleophile and directly displace your leaving group in one step, because that would be wrong. And if you do that, I'll point out that you did it wrong, and I'll say this is not SN2. That was a long time ago. We have lots of different substitution mechanisms now. Electrophilic aromatic substitution that's not SN2, nucleophilic acyl substitution. Later we're going to get to nucleophilic aromatic substitution. So there's lots of different mechanisms for substituting one group with another group in organic chemistry. All right, let's keep going here because I want to talk about what's the difference between an aldehyde and a ketone and a carboxylic acid derivative. Amides and esters and carboxylic acids, it's slower to add to those than to aldehydes and ketones. And that may seem weird. Why? Why do these kinds of substituents, OR and NR, slow down the addition of nucleophiles to carbonyls? So we're going to have to step back for a second and ask, what is it that makes a carbonyl reactive? So I'm going to draw this resonance structure for a carbonyl just to remind us that if you draw out a resonance structure for a carbonyl, you would take these electrons and give them to oxygen because oxygen's electronegative. And when I do that, I can see that this carbon here, this carbonyl carbon, is kind of like a carbocation. And now that I hope would make more sense, of course, you want to add things to carbocations. You want to add nucleophiles to carbocation. So if I were a nucleophile and I collided with this, it kind of makes sense that I would want to add to that carbonyl carbon. And I can use this other resonance depiction and draw exactly the same conclusion. Whether it doesn't matter which of these resonance structures I draw, my conclusion would be that I want to add to that carbonyl carbon. Okay, so you want to add carbonyl carbons because it acts like a carbocation. Now that if we're able to think of carbonyl groups kind of like carbocations, now we can think about two completely different and opposing effects of heteroatom substituents on that carbonyl group. So let me go ahead and redraw out this this carbonyl group. But instead of having a methyl on the other side, let me go ahead and put a heteroatom on the other side. So I'm going to take this carbocation resonance structure over here, and I'm going to use that to think about what would be the effect of putting an OR group. And there's going to be two completely different types of effects. There's an electronegativity effect, because oxygen is electronegative. And then there's going to be a lone pair effect, because oxygen has lone pairs. And those will have different influences on the reactivity of the carbonyl. So when I draw out this carbocation like resonance structure for the when I draw out this carbocation like resonance structure for an ester instead of a ketone, well, what's the effect of having an electronegative atom with lots of protons in the nucleus? Well, oxygen is electronegative. There's lots of protons in the nucleus. Let me just go ahead and write that there. Oxygen is electronegative. Can I fit this in here, the word electronegative? And having all those positive charges in the nucleus, the protons in the nucleus of oxygen, destabilizes this carbocation. So it makes it faster for nucleophiles to add into this carbocation center. So electronegativity increases the rate of attack. Let me just go ahead and write that down. Because OR is electronegative, electronegativity increases. Let me put it in capitals. Increases the rate of nucleophile attack. So let me go ahead and draw the nucleophile attacking there, just so we can kind of get comfortable with this idea that if you have some nucleophile, I'll give it a negative charge, that should attack more quickly. Well, let me use my red color here for that attack. So that carbocation center should be more reactive because oxygen is electronegative. But there's a completely different effect of the oxygen atom that has to do with the fact that the oxygen has lone pairs. So let me redraw this same structure and emphasize a different aspect of that OR group, and that is the fact that it has lone pairs. Let me draw that lone pair super big there. Right? And so the effect of the lone pair is that lone pairs donate into adjacent carbocations. Let me draw that donation using this curved arrow. So if you're a nucleophile that's trying to add into that carbocation, let me draw my pathetic nucleophile here, trying to add in, and there's already this alkoxy group that's physically attached adding in, it makes it harder to add. It's not impossible, it's just harder to add. I don't want to make it look like it doesn't happen. But how are you going to compete with that lone pair that's there all the time? So the effect of the lone pair, it's going to decrease the rate of nucleophilic attack. Two opposing effects. Wow, that's complex. The lone pair decreases the rate of nucleophilic attack. And so which effect wins? There's this effect of electronegativity that makes esters, carbonyls more reactive. Then there's this effect of the oxygen lone pair that makes esters less reactive. And so which effect wins? The simple answer to the question is that lone pair donation is more important. So let me just go ahead and write that down here. This effect is more important. More important than electronegativity. So because of this lone pair effect, esters and amides are less reactive than ketones and aldehydes, relative to having an H there. So when we see esters and amides, they slow down the rate of attack on carbonyls. I'll try to emphasize a little bit later why chlorine doesn't fit into this pattern And it's kind of simple, but it's not something you can visually see using simple Lewis structures in most depictions of those Lewis structures. So I want to talk about these major classes of carboxylic acid derivatives. So again, what we're talking about is the nucleophilic addition step. What's happening to the rate of step 1? That's the rate determining step. That's the step that if it's fast, your overall rate of substituting is fast. If it's slow, then you're not going to have a very fast rate. The rate at which you cleave out the leaving group is always fast. So, the leaving group doesn't have an effect on that type of leaving group step, doesn't have a super big effect on the reactivity of carbonyl groups towards substitution. I'm going to go ahead and give you some numbers here to help you think about the relative rates of substitution. How quickly do you add to carbonyl groups in carboxylate anions, in amides, in esters, in what's called an acid anhydride, and in an acyl chloride? And I'm going to compare all of them to an aldehyde. An aldehyde is not a carboxylic acid derivative, but we've already covered a chapter on aldehydes. So are these different functional groups, do you add to the carbonyl faster than you add to an aldehyde or slower? So I'm going to give you some numbers. My group recently published a paper, the first comparison to give you the ability to compare these numbers together. It's pretty powerful. Okay, so relative to an aldehyde, an ester is way less easy to add to the carbonyl. How much slower do nucleophiles add to the carbonyl? Well, in general, it's about 10 to the minus 5. Right? This is exponential, 10 to the minus 5, 0.0000. I'm lost already. How many zeros I said? It's a lot of zeros. So 10 to the minus, it's way less reactive than an aldehyde. And that's mainly because those lone pairs are really donating into the carbonyl. And amides are worse. Nitrogen lone pairs are even more reactive. So let's go ahead and get a sense for those numbers. Now, when we talk about amides, it's 10 to the minus 10. It's 10 billion times less reactive than an aldehyde. You need really powerful nucleophiles to add into an amide, if that's your goal, is to add into amides. And finally, maybe I should, let me see if I can try to figure out how to draw a different depiction of this. I'll try to redraw this sodium carboxylate so you can more fully see maybe a way to think about that. That's kind of like an O minus and a sodium plus. Now, there is a covalent bond there, but that O minus lone pair is so good at donating. I don't know, nobody knows it has a good quantitation on this, but whatever the reactivity is, let me switch back to the red pen here. Whatever the reactivity is, we're going to say that it's less than 10 to the minus 15. So way less reactive. Once you have an O minus right next to a carbonyl, it's hard to get to another nucleophile to attack that. Just very hard. Okay, but over here on the other side, I've got another type of oxygen derivative, this carboxylic acid anhydride. It looks a little bit like an ester. Right? See this oxygen here? Doesn't that look kind of like the ester over here? But it's not. It's not like the ester. This is actually more reactive than an aldehyde. And about how much more? It's about a factor of 10 times more reactive than an aldehyde. Now, it would be very uncommon for you to have an anhydride and an aldehyde floating around in the same reaction, competing for a nucleophile's attention. So I'm not sure that that's helpful for you to know that the carboxylic acid is slightly more reactive, is more reactive than an aldehyde, but you can remember that. Now, when we get to acid chlorides, I've tried to draw this depiction of the acid chloride with the carbon-chlorine bond freakishly long. And that's important because chlorine is not in the second row with carbon, nitrogen, and oxygen. It's in the lower third row, not the second row. That means the bonds are longer, they're easier to break, they're weaker, and it means that any lone pair donation that you might have seen back over here where the lone pairs are donating and decreasing reactivity of the carbonyl, that's just hard. That lone pair's so far away, you don't get effective donation. There's no effective resonance there with that chlorine lone pair. And so all you get is the electronegativity effect that enhances reactivity. And so we're kind of stuck in this situation where, not stuck, it's great, but acid chlorides are way, way, way more reactive than anhydrides, way more reactive than aldehydes, way more reactive than esters. And so this is why once you've synthesized an acid chloride in the lab, you can get anything to attack that, right? And they're also useful in electrophilic aromatic substitution. In general, this trend here, when you compare to aldehydes, the trend for carboxylic acids, and I'll just write this here, tends to parallel the basicity of the leaving group. So if you memorized basicity, maybe for some previous thing, so I'll say carbonyl electrophilicity. In a way, well, maybe I should say parallels leaving group ability, because it would be the opposite of basicity. Parallels leaving group ability. So what would be the leaving group in each of these substitution processes? If you're talking about the acyl chloride, the leaving group would be a chloride anion. Let me see if I can get this to the, and so this would be, that's a pretty good leaving group. You know, anybody who's taken a quarter of organic chemistry can recognize that chloride's a good leaving group. Maybe not so easy to recognize that a carboxylate anion is a potential leaving group. So over here, if I look at this carboxylic acid anhydride, the leaving group would be a carboxylate anion. Now, aldehydes are not carboxylic acid derivatives, so I can't really, hydride would never act as a leaving group. I'm not even going to entertain that. And a carboxylate anion is a more stable and better leaving group than an alkoxide anion. Alkoxides can act as leaving groups, just not in SN2 reactions. And that's a better leaving group than an amide anion. My gosh, that's just an insane to even think about as a leaving group. And there's no way we can have an O minus with a second minus on there, like 2 minus charges as a leaving group. That's just, what is that thing? It's an oxide dianion? I have never seen anything like that. That's crazy. Okay, so you have to memorize the relative order of reactivity here. And it's a result of two effects. It's the electronegativity of the atom and the lone pairs that are on that atom that can potentially donate into the carbonyl. And those two effects together lead to this huge difference, 10 to the 20 orders of magnitude range in the ease with which you can add to those carbonyl groups. All right. Let's go ahead and get into some of these reactions of carboxylic acid derivatives. And we're starting with acid chlorides, which are, man, they're so reactive. It's just, every organic chemist loves doing reactions with acid chlorides because they're fast, they work, the yields are high. And so the only thing we have to worry about here is how do we soak up the HCl byproduct in this reaction. So I'm showing you a reaction here where we take an acid chloride and an alcohol. And I made the alcohol chiral over here at this center just to show that, you know, you're not breaking or forming bonds. That bond doesn't break or form. So if you start off with in this case, it would be an S stereogenic center, then we're going to have an S stereogenic center in the product because you don't break any bonds to that carbon atom. Now, I'm not sure if you'll remember what was the base I said we needed to use here. We need to use something that can soak up the HCl. And the base that we use in this case is pyridine. So let me go ahead and write pyridine here. And I'll remind you of what is the byproduct you get. We'll talk about the mechanisms for these kinds of reactions shortly, but pyridine is not as basic as a regular amine. It's about 100,000 times less basic than a regular amine. We just use it to soak up the HCl so the HCl has somewhere to go. Because we don't want HCl floating around in our reaction, you know, catalyzing substitutions of the alcohol or doing some sort of thing like that. We want the conditions to be relatively not super acidic. Okay, when we want to make amides, we can do the same type of reaction. In this case, if we want to make an amide bond over here, like this, we just add that amine in. Here's that same amine, and instead of having a carbonyl group on there, we just have an H. You can see that we're going to lose H and Cl out of this reaction. And so we just need something to soak that up. It can't be pyridine, right? Pyridine isn't, if we put pyridine in here, this would get all the protons from the HCl, because this is about 100,000 times more basic than pyridine. So we need a base that's just as good or better than that amine. And triethylamine is the common organic base that we use in the laboratory. Everybody who does organic synthesis uses triethylamine a lot because it's organic, it's soluble in all organic solvents. Unlike sodium hydroxide, nobody would use that. It's not soluble in organic solvents. Um, so triethylamine is kind of a go-to base, and it's 100,000 times more basic than pyridine, which is another common base. So the byproduct here in this case is triethylamine, except it's protonated. I'll draw the bond to the proton there. Triethylammonium chloride. We're going to have a whole chapter on amines coming up in 3 chapters from now. We'll talk about the acid-base properties and equilibria for protonation. So again, when you're making amides, you use triethylamine as your base. If you're making esters from acyl chlorides, you use pyridine as your base. Now the book tells you, and this is not very realistic, but they tell you that in theory, you could take your acid chloride and you could simply add extra amine. And there's a very few cases where that makes sense to do. So let's just suppose I want to make an acid chloride from ethylamine. In this case, ethylamine would be so cheap that you could simply add excess ethylamine. And that's true. So another set of possible conditions here would be just to use an excess of your amine. That's a useful set of conditions. Let me make the acid chloride more complex, because otherwise we're not getting a sense for how tolerant these conditions are. I'll go ahead and put a 3-carbon backbone. It's propyne. I'll put a chiral center, an asymmetric center here, just to show that we're not breaking or forming any bonds to this stereogenic center. So it's going to be still there in the product. I'll go ahead and draw the product of this reaction. This is starting to look like real organic synthesis to me. And in this case, as long as the amine is inexpensive and you can buy bottles and bottles of it, who cares whether we're also using it as the base in this reaction? Because you're going to throw away this ammonium chloride salt. And that's okay if it's an inexpensive amine. But in the cases up above here, like this, in this case up above here, that's not inexpensive. If it's chiral, that probably costs quite a bit of money. You wouldn't want to use that as your base for the reaction, because that means you're only 50% of it is reacting to form a nitrogen carbon bond. So, so these conditions of using excess amine really are only common. It's only I would just say only common if the amine is simple and cheap. And how would you know if it's cheap? Well, you wouldn't know that because you'd have to go look it up in a typical chemical company catalog. But if it's structurally simple, like with not more than a few carbons on there, would be like a methyl and an ethyl or 2 methyl groups. Very rarely would you use those conditions. Okay, so far more common is to use triethylamine as the base for those reactions. All right, let's go ahead and talk about the mechanism for this substitution reaction. And it's going to be the same mechanism whether we're adding in an alcohol or an amine. I'm going to show you the mechanism when it's an amine attacking, but if you want, go ahead and put the alcohol, replace R2NH. The point is they both have these nucleophiles with a lone pair in there. So if you want the mechanism for the alcohol making the ester, just replace R2N with an RO group. So what's the first step? It's going to involve an addition and an elimination somewhere in the mechanism, but there's going to be some extra stuff in there related to proton transfer. Of course, it's going to start with addition to that super reactive acyl chloride. My gosh, that acyl chloride is reactive. And amines are nucleophilic and basic. Let's go ahead and draw out this next synthetic intermediate here. I'll draw the carbonyl carbon with the elemental symbol C. Here's our chloride leaving group. And here's our nitrogen atom. We just made a new bond, new nitrogen carbon bond. 4 bonds to nitrogen. You have to have a positive charge if you have 4 bonds to nitrogen. So now we're going to end up with this switterionic intermediate. And whether we've just added an alcohol or a water or an amine in, we have to deprotonate the N plus or the O plus. We have to deprotonate that before we kick out the chloride. And so this next step is really describing what is the role of the base, whether it's, in this case, triethylamine or another amine molecule, or in the case of making esters, if it's pyridine. We've got to deprotonate this as part of our arrow pushing mechanism before we make the chloride act as a leaving group. So let's go ahead and draw that happening. And you couldn't have known that. This is something where you just have to memorize the mechanism, the order of steps that I'm telling you. So then after we deprotonate that, now we can push out that chloride leaving group. My gosh, you couldn't stop that chloride from leaving. So now we have lone pairs over here on that O minus, and we don't have a positive charge nearby. And now we're simply going to push out that chloride leaving group. So this is the elimination step. Let me make sure I make the arrow end here on the carbon atom, because on our sapling system, we ask you to make arrows end on atoms. And so now we get this amide functional group as our product. And the chloride is now the leaving group in that process. And whatever the base was is now, since it was neutral B before, I'll make it a positive B. So that's the mechanism for making esters or amides using alcohols or amines, respectively there. It's a three-step mechanism, and the second step is this proton transfer. We have to deprotonate the atom, the nucleophilic atom that attacked before we kick out the chloride leaving group. Go ahead and practice this using the alcohol molecule. It's the same mechanism, but I think it would help you to see that it's the same thing, just more practice is better. All right, that's it for our getting started on this whole chapter on carboxylic acid derivatives. Just a bunch of taking amides, esters, carboxylic acids, acid chlorides, and anhydrides and converting them back and forth into other carboxylic acid derivatives. And it's not one-step SN2 chemistry, it's addition and elimination. And there's proton transfers thrown in here to just add a little spice to that.